Since the dawn of humanity, man has looked up the night sky into the stars and wondered, what is the true nature of the universe? In 1473, one such man was born. His name? Nicholas Copernicus. Up to that point, those semi-rational models of the universe were still geocentric, meaning that they described all the stars and planets as revolving around the Earth, the place where we humans resided. Copernicus' ideas, however, presented a so-called heliocentric model, a model in which the Sun was a stationary object and the Earth and other planets revolved around it. Sadly, people had great trouble accepting his ideas at the time, despite the fact that at the end, they turned out to be true. The Earth really is making revolutions about the center of the Sun, and Copernicus was also starting a revolution of our approach to understanding nature. Towards the end of the 19th century, this approach culminated in a model that went something like this. Within space and time exists matter made up of discrete particles with a given mass. Any such particle may change its position in space with respect to time. This is called motion, and the thing that causes or changes motion is called force. Forces act on particles and make them move. For any such system of particles and forces, there are certain symmetries that are respected and hence quantities that are conserved, such as linear momentum, angular momentum, and energy. Back then there were two known fundamental forces, gravity and electromagnetism. Gravity acts on all particles with mass, while electromagnetism acts on particles which possess a property called electric charge. When a charged particle oscillates about a point, it causes a disturbance in the so-called electromagnetic field that propagates in the form of an electromagnetic wave, or simply light. Hence, light was thought to be a wave. This was proven even further by the famous double-slit experiment, where light was shown to form an interference pattern, an effect that was only exclusive to waves. At the turn of the 20th century, however, the famous physicist and scholar Max Planck was studying the emission and absorption of light when he discovered something that would change the course of scientific history. Light can only be emitted and absorbed by a discrete amount. It didn't take long for young Albert to propose that maybe it's not just the emission and absorption, but perhaps light itself that is quantized, i.e. made up of discrete particles called photons. The truth, however, was that there was strong evidence for both the wave and particle nature of light, so physicists decided that it's better to think of it as both. This was the birth of quantum mechanics. In quantum mechanics, particles are described by their so-called wave function, and the evolution of that wave function by the now famous Schrödinger equation. The wave function is a mathematical formalism which tells us only the probability of a given particle being in a certain state. Hence, a particle can be in a superposition of states, where for example there's a 50-50 chance of it being in one of two different states. Prior to observation, it was said to be in both of these, however after observation the particle collapses into a single definite state. Therefore, it was thought that observation or measurement, which is the entanglement of the observer's wave function with the wave function of the observed, facilitates the transition from quantum indefinite information to classical definite information. But the weirdness doesn't end there. The condition of the observation of a momentum and its corresponding position are incompatible. To observe the position of a system as precisely as possible, we must observe it with light or electron waves or similar means of high resolving power or short wavelength. However, the light has a particle action depending on its frequency only, and to illuminate a body with high frequency light means to subject it to a change in its momentum, which increases with the frequency. On the other hand, it is low frequency light that gives the minimum change in the momentum of the particle it illuminates, and this has not a sufficient resolving power to give a sharp indication of positions. Intermediate frequencies of light give a blurred account of both positions and momenta. This is the Heisenberg uncertainty principle, and it is also applicable to the notions of energy and time. The more precisely we know the energy of a given quantum system, the less precisely we know how long it has that energy, and the more precisely we know the time a system exists in a given state, the less precisely we know the energy it possesses in that state. This immediately results in the mind-boggling concept of quantum fluctuations at the smallest timescales. At these scales, temporary random changes in the amount of energy in different points in space occurs, despite those being in a vacuum. This is the quantum foam, the prima materia as the alchemists might have called it, a scale of pure potentiality where virtual particles come in and out of existence. Perhaps the Big Bang itself resulted from a giant vacuum fluctuation. However, that is a topic for some other time. Parallel to the development of quantum mechanics, another great theory of reality was being cooked up by yet again Albert Einstein, who in 1905 published what is probably the most famous paper in scientific history, on the electrodynamics of moving bodies. In it, he followed the consequences of two simple postulates. First, the laws of physics are the same in all inertial frames of reference, and second, the speed of light in a vacuum is the same in all inertial frames of reference and is independent of the motion of the source. What followed from this was his special theory of relativity. In it, space and time are unified into a single entity called spacetime, with three spatial dimensions and a single temporal dimension. This allowed for the replacement of the classical Galilean coordinate and velocity transformations with the relativistic Lorentz transformations. The consequences of this were the strange effects known as time dilation and length contraction. Both occur when an object's velocity approaches the speed of light. For such an object, time seems to slow down, and its length parallel to the motion seems to shorten. Special relativity also introduced us to the famous equation E = mc squared, telling us that rest energy and mass are convertible, and expanding the law of conservation of energy to the more general conservation of energy and mass. What Einstein really did was he unified both space and time, matter and energy. He showed that the experience of space and time is dependent on the observer's frame of reference, and he also proved that no object with mass can travel at light speed, because the faster an object goes, the heavier it becomes, and the heavier it becomes, the more energy you need to accelerate it. For an object with mass to travel at light speed, it would need an infinite amount of energy to do so. Later, Einstein expanded his special relativity to include objects undergoing acceleration. This new theory, called the general theory of relativity, demonstrated that acceleration and gravity are indistinguishable, the equivalence principle, and then explained gravity as the result of the curvature of spacetime due to massive objects. If you imagine space as composed of parallel grid lines, then a material object would bend those lines towards it, causing objects moving in a straight line to seem like they are being pulled, when the truth is the straight lines of space are actually not straight. Because time is also curved, this causes objects at rest to also experience the effect of gravity. One experimental proof of this theory is the fact that light, which always takes the shortest path, i.e. a straight line, still bends around massive objects, making us come to the conclusion that space itself must be curved. Overall, it isn't very difficult to see why we use the name of Einstein as a synonym for genius. He made massive contributions to the field of quantum mechanics and formulated the theories of special and general relativity. But there was still a problem. Quantum mechanics, as initially presented by Heisenberg and Schrödinger, didn't account for the rest energy of particles as implied by special relativity, and hence for their creation and annihilation. Through the century, however, with the work of great physicists such as Paul Dirac, Richard Feynman and many others, a new theory emerged that was able to unify both special relativity and quantum mechanics into a single coherent framework. This was quantum field theory. In quantum field theory, particles are described as excitations in what are called quantum fields. To understand these, try and imagine a one-dimensional oscillating string. This string is going to have a certain amount of energy proportional to its frequency of oscillation. Now try to imagine the same scenario but with a two-dimensional membrane. Now, with a three-dimensional field, to which you can assign such a quantity of energy at every point in space and time. We are now going to turn this into a quantum field by setting a minimum amount or quanta of energy. This restricts energy to either be an integer multiple of this quanta or a single quanta, but never less than or a fraction. For the electromagnetic field, the quanta was the photon. The theory that describes the electromagnetic interaction is called quantum electrodynamics. It affects particles with electric charge, which can either be positive or negative. Opposite charges attract and like charges repel, and they do so by exchanging virtual photons. Thanks to quantum mechanics and scientists like Niels Bohr, we now have the widespread model of the atom, the so-called building block of matter. It consists of a nucleus made up of protons and neutrons and electrons surrounding this nucleus. The electrons have a charge of -1, the protons a charge of +1, while the neutrons have no charge. The electrons are attracted to the protons of the nucleus and are usually the same number as them to form an electrically neutral atom. If a photon collides with an electron, the electron can absorb its energy and get promoted to a higher state. However, then the protons can pull it back in, causing it to emit the photon back out. You might ask, how are the protons in the nucleus held together as they should be repelled by their positive charges? The answer is that they are held together along with the neutrons by a stronger force, called, rightfully, the strong nuclear force. The study of the strong nuclear interaction is called quantum chromodynamics. It tells us that, unlike electrons, protons and neutrons are not fundamental particles, but are themselves composed of even smaller particles called quarks. There are two types of quarks: up quarks, which have an electric charge of +2/3, and down quarks, which have an electric charge of -1/3. The proton is composed of two up quarks and a single down quark, while the neutron is composed of a single up quark and two down quarks. As you can see, their charges add up to 1 and 0 respectively. However, quarks possess another type of charge called a color charge. This has nothing to do with actual colors, but is another fundamental property of matter, and the strong force acts on it. There are three types of color charge called red, green and blue. The same way opposite electric charges cancel each other out, the three color charges when brought together also cancel each other out to form a particle of neutral color. Unlike QED, QCD is a much more complex interaction. However, the underlying mechanics are pretty much the same. The strong force also has its own field with its own particle of quanta called the gluon. Gluon, as it glues quarks into protons and neutrons, along with protons and neutrons into a nucleus. It's again mediated by an exchange of virtual gluons and is subject to the actions of emission and absorption. One major difference, however, is that unlike the electromagnetic force, which decreases with distance, the strong force becomes stronger as the distances between the quarks grows, although they can be pulled apart with enough energy. The last of the fundamental quantum forces is the weak nuclear force. It is responsible for the phenomena of radioactive decay, specifically beta decay. The weak interaction is called weak because it acts at very small scales. It can affect quarks and another type of particle called electron neutrino. When a neutrino gets close enough to a down quark, it transmits its force carrier particle called the W boson, which has a negative charge. This causes the neutrino, which has no electric charge, to turn into a negatively charged electron, and it also causes the down quark to gain charge, turning it into an up quark. This then may cause a neutron to turn into a proton, and hence to transmute one type of element into another. The interaction may be more complex, but at this point your head may be spinning. Don't worry. All of these different particles can be united through something called the standard model of particle physics. Here you have 17 distinguished particles, each with their own corresponding field. On the left side there are the matter particles called fermions. These exist in so-called 3 generations, each differing only by their mass. The electron neutrino, and their corresponding heavier counterparts are grouped under the name leptons and are distinguished from the quarks as they do not interact with the strong force. Different particles may have different electric and color charges, mass, and another property called intrinsic angular momentum or spin. This doesn't mean that the particles are spinning per se, but is related to the direction of the axis to which the particle aligns with the measurement device. It can be represented as up or down. Both the charges and spin are conserved quantities, meaning that in any interaction the amount of charge or spin coming in is the same as the amount of charge or spin going out. On the right side of this table there are the force-mediating particles called bosons. The gluon for the strong force, the photon for the electromagnetic force, and the W and Z bosons for the weak force. All of these are called gauge or vector bosons and are distinguished from the scalar boson called the Higgs. The Higgs field is responsible for giving mass to the fundamental particles. The gluons and photons are massless, so they travel at light speed. All of these bosons have a whole integer spin, unlike the fermions, which have a spin of 1/2. The fermions obey the Pauli exclusion principle, meaning that two of them cannot exist in the same place at the same time. The bosons do not obey this principle. Lastly, all the matter particles have an associated antimatter particle with an opposite charge. When matter and antimatter come together, they annihilate each other, releasing loads of energy in the process. And that's pretty much most of it. The periodic table of our quantum fields. Personally, quantum field theory makes me think of the ancient Greek philosopher and mathematician Thales. He is known to be a mark for the transition from mythology to philosophy because of his idea that everything is made out of water. The reason is that it was a huge step moving from a highly anthropomorphized model of reality into one in which everything is reduced to a single substrate. This allowed then for Democritus to propose that everything is made out of atoms and void. However, it might turn out that Thales was also quite on point, as the nature of the now thought quantum fields resembles that of a fluid. The truth of the matter is that at very high energies, all the fundamental interactions merge into a single force called the grand unified force, a single field. Sadly, this does not include gravity. Gravity, as explained by general relativity, is incompatible with QFT. The reason is that the mathematics of curved spacetime and of quantum fluctuations and superpositions do not agree with each other. To resolve this, we will need a fuller, more comprehensive theory. A theory of quantum gravity. But for that, we might have to wait a bit longer.